Today's lesson is on derivatives of trig functions. We'll review some of the derivatives from the memorization sheet. The blue memorization sheet lists all of the trig function derivatives on it. We'll also look at a few types of applications using trig derivatives and a few examples. The main part of the lesson is looking at the derivatives of the different functions. The derivatives of the functions, again, are on the blue memorization sheet. The derivative of sine, for example, is cosine. What this means is that when you graph the function, its derivative looks like exactly another function that's a trig function. For sine, it happens to be cosine. Here's an example of a typical problem that would use the derivative of sine or cosine. Derivative of cosine, notice, is negative sine, or the opposite of the sine function. So here's an example. If we have 1 plus x minus cosine of x, the derivative of 1 is 0, the derivative of x is 1, and the derivative of cosine would be negative sine. So the derivative of negative cosine is positive sine. So this would be our derivative answer. Here's another example. Find the derivative of sine of x over the cosine of x minus 2. If we use our quotient rule, u over v, we take v, cosine of x minus 2, times the derivative of sine, which is cosine of x, minus sine of x, which is u, times the derivative of cosine is negative sine of x. Derivative of negative 2 is 0. All over v squared. Leave the denominator alone. The numerator can be simplified. When you simplify the numerator, we want to combine our terms. So I'll distribute the cosine. That would give me cosine squared of x minus 2 cosine x, and then plus sine times sine is sine squared. So now we're at this step in the steps listed on the left column. Probably our most popular trig identity, sine squared plus cosine squared is 1. So we're going to combine the cosine squared and sine squared into 1, and then the rest of it we write. So here's our derivative. Again, just leave the denominator. An example of using a trig derivative is the motion of a weight bobbing up and down on the end of a string. This is an example of what's called simple harmonic motion. We'll discover and take a look at different types of motion as we go through the rest of Chapter 3. Here's an example using a trig function. A weight hanging from a spring bobs up and down with position function at 3 sine of t. What is its velocity and acceleration? We haven't studied all of the terms for the particle motion yet. However, we can still take a look at derivatives. Here's the function. Here's the first derivative. Derivative of 3 sine is 3 cosine t. And then the second derivative the derivative of 3 cosine t is negative 3 sine of t. So here's an example of where we would use a trig derivative. Another place we use a trig derivative is what's called a jerk. A jerk is the derivative of acceleration. So this would be an example where we would not only use perhaps a trig derivative, but also where we would have an example of a third derivative. We'll study the jerk more when we look at particle motion. Here are some other trig derivatives. Again, all of these trig derivatives that are in the yellow box are on your memorization sheet. Here's another example. Find an equation of a line tangent and a line normal to the graph of y equals sine of x divided by x. Let's focus on our derivative, and let's find it at the point x equals pi over 6. We'll use the quotient rule to find the derivative. We start with our v times derivative of tangent is secant squared minus tan times derivative of x is 1 divided by x squared. So this is dy dx. Plug in pi over 6. Remember that secant is the same as 1 over cosine. So we'll put it this way in the calculator. Minus tan pi over 6 over pi over 6 squared. We look at our derivative then and evaluate the derivative, which again, if we look back at our derivative, we had our dy dx equals x times secant squared x minus tan x times 1 all over x squared. Plug in or evaluate at pi over 6, and we get a slope of 0.441. If we find the y value when x is pi over 6, y would equal 1.103. And let's use all decimals, so let's take a look at what is pi over 6, which is 0.524. Now I write my equations. Y minus the y value equals slope, x minus the x value. And if we do the same thing for a normal line, we do the opposite reciprocal slope. Y minus the y value, negative 1 over 0.441, x minus 0.524. And that one's done. Here's another example of a trig derivative. If we follow along with this example, we have x cosine x, so we're going to use our product rule. We use the product rule, we have u times derivative of cosine is negative sine, plus, so u dv plus v is cosine, du is x. And evaluate that at 1, so if we plug in a 1, we can see the work. Here's the y and the slope. Our equation is right here for solving. Here's the picture of that function we just looked at and its tangent line. Let's find a second derivative. Derivative of secant tangent. For the second derivative, we have to use the product rule. We have two different functions multiplied, so we take u times derivative of v plus v times derivative of u. Simplify it. Secant to the third, or cubed, tangent squared, secant. And that's our derivative. Second derivative. And that's it. That's our lesson for today.